or warming. Hello, good morning, good evening, good afternoon, everybody, wherever it might be. It is my great pleasure to welcome Lucas Hall, all the way from Haifa, right?
Yep.
He will tell us everything and more about topological classification of Skew products for Quiver sister algebras, which are possibly also known as graph sister algebras. It's
Not exactly.
Not exactly. Okay, so we'll find out the difference. It's all yours. Take it away.
Excellent. Well, thanks first of all for the invitation and for all of the efforts that the organizers put in making this this great seminar take place. It's a faithful part of the organization of operator algebras around, and so it's really a pleasure to be here. Yeah, so I'm going to be talking about a something that is really well motivated, I guess, by the typical paradigms that we have in operator algebras of this kind of relationship between topological phenomenon and how this can be translated into an algebraic framework that is really sheds a lot of light. And something that I particularly like about this particular topic is that usually this analogy is sort of loose because you say, okay, well, we know how things work in the classical setting with topological spaces and these kinds of things. We know how to translate that to abelian C-star algebras. And we just take this as kind of as an inspiration. But something that's exciting about this particular topic on Quiver C-star algebras and this topological classification is that really, in a sense, this analogy is not just inspiration. It's much closer to being true. So I'm really excited to be sharing some things about that. So the way we're going to go about this is going to split this lecture about in half, I guess. It's going to have some topics on topological phenomena that we're going to be studying, like well, Quiver C-star algebras, and I'm actually going to start with some bundle theory to get us in the right mindset. And then in the second half of it, I'm going to bring in all of the operator algebras and see how some of the things that we talk about in the topological setting they end up being well-founded in the non-commutative context as well. So with that, we're going to go ahead and get started. So to start, I want to just introduce the notion of a bundle, which is a triple of 3 bits of information, 2 of them being a topological space, which I'm denoting here by E1 and E0. And the second bit of information being a continuous surjection. And so at its face, this looks like, maybe why are we giving a different name to a continuous map, which is the morphism in the category of topological spaces or something like this? And the idea is that we're kind of approaching this idea of a topological space with a little bit more nuance, with a little bit of a different perspective that is going to give us a little bit of support as we proceed. So as far as names are concerned, we're going to call in this setting E1 the total space. That's the space in the domain of this continuous surjection. E0 the base space, and this map P is going to be the bundle projection. Okay, and one important aspect, one thing that people like to study in particular about bundles is what happens to the preimages of individual points. And so we give a special name to these things. If you're a point in the base space V, then the fiber over V is defined as the set of all points which map to it, right? The preimage of that point under this continuous surjection. But well, this is all fine and good, but I think that pictures help a lot to elucidate some of this information. So I've included a number of them. So right in this philosophy, sure, we've got a continuous surjection P, which goes from this space, this total space, to this base space. And the principle or the idea, or how at least I like to think about these bundles and these bundle projections, is somehow this total space is suspended over the base space, right? And so we have this map that says, okay, well, this total space somehow fits together in some well-defined way into the base space entirely. That's why it's surjective. And the idea is if you choose any particular point in the base space, then you can investigate, okay, what are all the points in the total space which are kind of supported over that single point, right, under this projection. That's kind of the idea of it. And of course, if you choose different points, then you're going to get different pre-images. And the idea is that somehow these fibers over the points in the base space they patch together in order to give us what the total space actually looks like. That's kind of the principle of it. And so, okay, well, the total space is actually patched together from a bunch of smaller subspaces, which are these pre-images, these fibers over the points in the base space. So something that's someone might care about, something that we're going to care about in particular is, what's the volume? How much space is taken up by a particular pre-image? How much is actually, maybe we'll just leave it at that. How much is taken up by a single pre-image point? What's the volume of this fiber in the total space? And so this brings us to this notion of a full piece system of measures. So what you do is you take a bunch of measures which are defined on your total space E1, and they're subject to a couple of conditions. Well, one thing that I want to point out is that this family of measures is actually indexed by the base space. Is something that we're noticing. So associated to each point in the base space, you have a measure on E1. Well, and what would we like it to do? Well, we'd like it to measure the volume of the pre-image, is the idea, right? So this is the first condition. We say that the support of any one of these measures, lambda v, lambda indexed by v, is equal to the entire pre-image of that point. And then the second thing that we would like is we would like to have a notion of continuity, because this is one of the best features that we could kind of hope for in a topological setting. So what we insist in this context is that whenever you have a continuous compactly supported function defined on the total space, then there's a nice continuous way to assign this particular map. If you give me two vertices or two elements of the base space, I should say, that are nearby, and I integrate this continuous compactly supported function against the measures which are associated to each of these points, the closer these 2 points are to each other, the closer the values of these things should be, right? So in this way, there's these measures which are measuring the volume of these patches in the total space. Somehow they assemble in a way that gives you some appropriate notion of continuity. Okay.
That's a silly question. Is it obvious that fibers are closed?
Is it obvious that fibers?
Like P1 of the.
Was the topology of the base?
Yeah, I mean, okay, that's true. I mean, yes.
Topologies.
Because when I see support, I would assume that support is something closed. And then right, that is equal to the fiber.
Yeah. So for measures, right, you could even just take the closed support if you want to be really, really careful about it. So I guess here I do mean the closed support of this measure.
Okay, so in your setting, fibers are closed or not?
Well, yeah, because this is a pre-image of a closed set, right?
Well, I mean,
Points are closed.
points are closed. You said nothing about the topology of E0. It can be very non-T1, non-T0, whatever you want.
Oh, no, you want it. Okay.
You never said Hausdorff.
Hausdorff.
Okay, fine. So let's play fair, and we'll say in this setting, all of our topological spaces are going to be locally compact, Hausdorff, and in fact, second countable as well.
Locally compact, Hausdorff, second countable. Okay.
So yeah, so in particular, the pre-images of any of these points are closed. And so yeah, as I was saying, the whole principle of this P system of measures is we get a continuous map out of any one of these continuous compactly supported functions on the total space, which is given by just the way that the total space is broken up. Okay, well, we have measures for each of these pieces, and if we measure a continuous function against each of these individual pieces, then we end up with something continuous at the end as well. Okay.
Is it automatic? Sorry, I have a question. Is it automatic in your setting that these measures are radon measures?
I should say yes. A family of radon measures is also going to be important for us. This is part of the assumption.
Okay.
Of course, we'd like them to respect the topology as well as we could hope for a measure 2 anyway, right? So here's another picture which kind of illustrates the general idea. Once again, we have the total space, that's this entire rectangle, which I'm viewing as being suspended over the base space, which is just this horizontal line down below. And I see illustrated here that we've got these vertical lines which, you know, have these different colors, right? So the idea is that if you look at this orange point in the base space, you look at the pre-image, okay, well, that's going to be this entire orange line. And the idea is that the support of the measure is pretty much, it's going to be this entire interval, if we're thinking honestly about it. And not only that, but the second condition that we have is about this continuity for these measures. The idea is that, okay, if you had some continuous function which was supported on this entire rectangle, then okay, as you march from orange to red to purple to blue, right? We see that I'm kind of giving the impression that we've got an accumulation point forming here. Okay, well, as you get closer, then you're going to get closer values for the integral, even if this continuous function is allowed to deform over the elements of the space. Okay. So once again, we're seeing that we've got this total space, which is being split up into a bunch of closed subspaces. And somehow we have a notion of how to measure the volume of those subspaces and patch them together in some appropriately continuous way. So now I want to talk a little bit more about some things that we can do with bundles. And this is going to lead us into bundle morphisms. So suppose that you have two of them. You've got a bundle which is given by EPB and another given by topological space FQC. Then a bundle morphism is going to be nothing more than a pair of continuous maps, one continuous map going between the total spaces, so from E to F, and the other continuous map is going from the base spaces from B to C. So in this context, when we think about a bundle morphism, the way that I've defined it, the first bundle, EPB, this is the domain bundle. And then the second bundle, FQC, this is the codomain bundle. And what we require of them is that these computations that I've written here are exactly the same. That if you take F, which moves you from the domain total space to the codomain total space, is composed with the bundle projection for the codomain bundle. This better be the same thing as if we had taken the bundle projection for the first bundle and then moved along G. And another really important, for us especially, a really important construction that we can do with the bundle is we can construct a pullback. So if you've got, you know, some ambient bundle that you're interested in this case, I'm calling it FQC, and I've also got a continuous map which goes from the base space of that bundle that I just described to some auxiliary space B. Then I describe the pullback under G. It's this particular subspace of the Cartesian product, which essentially we'll see in just a moment that it's really arranged so that the fibers are behaving in a really, really kind way. It might not be abundantly clear from how this is described, but we're going to see in just a moment that really this is saying something very, very nice about controlling the fibers of a particular thing. And in particular, this pullback bundle, G star of F, or this pullback object is a bundle with base space B and with total space exactly the pullback, the projection being the projection onto the first coordinate. And the pair given by the projection onto the second coordinate over the total spaces, and G, this map that we're pulling back under to begin with, is actually going to give us a bundle morphism between this pullback bundle and the original bundle that we started with. Okay, so let's take some pictures to really get a sense of what's going on with these bundle morphisms first. Okay, so we've got two of them, one on the left with lots of curvy edges and then or curvy lines, and then one on the right that's a little bit more sharp. And so what exactly should a bundle morphism be? It should describe for us how this composition works, right? If we apply F to move along the total spaces and then apply the quotient map, that better be the same thing as we apply the bundle projection and then project over to the codomain base space to begin with. And now the way that I've described this picture, this kind of makes it clear that one of the jobs, or maybe the job of a bundle morphism, is to say, okay, well, if you're looking at the fiber of a particular base point in your domain total space, all that we're asking for is that this thing has to map into the fiber of the codomain total space over the fiber which is associated to the image of that original base point that we started with, right? So everything in the total space that's a fiber over B exactly gets mapped into the fiber over G of B. This is the idea. This is what a bundle morphism gets for us. And now for a pullback, we're gonna take a similar kind of picture, right? So we've got this bundle project or this bundle FQC, and we've got this auxiliary space which I called B in the slide before, and we've got a map which goes, a continuous map which goes from this auxiliary space into the base space of the bundle. Great, well then what should the, how should the fiber bundle be constructed, or how should the pullback bundle rather be constructed? Well, in this context, what we'd really like is we'd like to study again the fibers over some point. Okay, let's start maybe in the auxiliary space. Given B, we map that under G to our base space, and we ask, what's the fiber of that space? Then what this pullback does is it literally pulls back that whole entire fiber, and it says, okay, well, this is what we're going to assign to be the fiber over this point B in the pullback bundle. This is its exact job. And this second point here, the idea is, okay, suppose that this map G, say, isn't injective or something like this, and that this point on the left and this point on the right are both mapped to G of B. Well, then the principle is that, okay, both of those fibers are actually going to be identified, or shall I say identified? No, I should say that we get two copies of the same fiber in this context. That's kind of the idea of it. And even though I've made the shape reverse, the idea is, okay, these are trapezoids, the same shape, the fibers are exactly the same. This is the job of a pullback bundle. It says, okay, I want to assign the fibers of this bundle to this auxiliary space, and I'm going to construct it in exactly this way. Okay, so now I want to talk about G bundles. We're going to keep kind of building up and scaffolding all of these ideas until we have enough to work with. So now we're going to start with a locally compact group. This is going to be second countable for the sake of the rest of this talk. But I don't know that this is, in fact, terribly important. It's only for logistical reasons that we're going to insist that this group G is second countable as well. Okay, and we want G to act on this, on some topological space E. Okay, it's called a G bundle, or we define a G bundle to be a bundle where the total space is this space E that G acts upon. And we've got some, continuous surjection Q onto some base space. And what we know is topologically, at least, that the base space is homeomorphic with the quotient of E under the group action, right? So things can get a little bit fussy. And how I like to think about G bundles is a G bundle is pretty much an orbit map in disguise. It's pretty much an orbit map in disguise. But it's maybe just a little bit more loose because we don't insist on equality, right? We insist on, okay, well, there's some kind of a homeomorphism and things can get just a little bit touchy. Now, an action of E on a an action of a group G on a topological space is called principal, provided the action is both free and proper. So free meaning that if you're not the unit, then if you're a group element that's not the unit, then you move everything in that topological space. And proper meaning specifically that a particular map which is associated to the action is proper, meaning that the preimage of compact sets are compact. But really the point is that these actions are particularly nice. That's a particularly nice class of actions. And
may I quickly comment on this definition?
Sure.
So it's my favorite definition, and I'm very happy that you put it this way. The only thing which I'm used to is that I'm more of a rightist than a leftist. You are evidently a leftist because you act on the left. So we have different political views, it seems. But silly jokes aside, you see, the original definition of principal bundle, due to Henri Tatin, was given in terms so-called translation map. So because of your freeness assumption, the translation map exists, which means that for any 2 points in the same fiber, you can uniquely assign a group element which maps one to another. That comes from the freeness. But now, what about topological properties? And Henri Cartan called them FP1 and FP2, fibre, principal, whatever. And one of them is that the translation map is continuous. And another one is that the image of a translation map is closed. And that's sorry, I'm not the image, sorry, I'm the domain of the translation map is closed because the domain of a translation map is a fiber product. So inside the Cartesian product of the total space of a bundle of itself, you have a fiber product of all pairs which are in the same fiber. And this need not be closed. It have very nice free actions with continuous translation map where this domain of a translation map is not closed, like the rep foliation. And amazingly enough, the fiber product is not closed inside the Cartesian product. And amazingly enough, original Cartan's definition is equivalent to this one.
And in fact, it's exactly this translation map that we insist is proper. So that's the whole idea. And really the punchline is that, okay, well, that means that this action is particularly well behaved. And in particular, it also means that this G bundle is particularly well behaved. And so we give a special name to these and we call them a principal G bundle. And then now, okay, so we've talked about morphisms of bundles. Now we're talking about G bundles. Well, a morphism of G bundles is simply a bundle morphism, but we insist that that map of total spaces is actually just equivariant for the G action. And one thing in particular that I'll say about principal G bundles is that the fibers are actually very, very rigidly defined for these particular bundles, in the sense that, in particular, if you take the fiber over any point in a G bundle, and remember what I said before, that this that a G bundle is kind of a quotient map in disguise. So it turns out that the fibers of a principal G bundle are always homeomorphic with the group G. This is a very, very, well, we'll see how this maybe comes to light in a little bit later in this talk. Well, I've got a couple of pictures for this too. Okay, so so we've got two examples of G bundles here. The first one is this red rectangle, which seems to be projecting, well, first of all, it's divided into 6 squares, and all of those squares project down to a single square. And we can see that there's, well, maybe I'm using my fibers here to actually define what I mean by the bundle projection, right? You take a point in any one of these squares, and it's going to map down exactly to the exact same point in the rectangle. And I claim to you that this is a G bundle, where, okay, well, now I've just said that the fibers over a G bundle are homeomorphic with the group G. And so, we've got a group with 6 elements. So what's going to be the group? It's going to be Z6. So that's one thing that we notice on the left-hand side. Now, on the right-hand side, things are a little bit more curious. Because, okay, at least as long as we're on this blue ray, which is radiating out of the center of the circle, we see how we can get a projection onto the black ray, which it's suspended over. But for every other point, we need to be maybe a little bit more clever. And the idea is that, okay, well, why don't we just wind back whatever element we have to this blue line, and then we can project down after that, right? Well, this winding, right, this is an action of the circle is what we're actually looking at. And something that I want to point out to you is that this action of the winding of the circle is well behaved almost everywhere, except for at this origin, there's kind of a problem, right? This isn't a free action because the origin just happens to be really, really poorly behaved. So the action on the left turns into a principal action, and this is a principal G bundle, where this action on the right-hand side is not. It's a G bundle, but it's not a principal G bundle. Just to see that not everything is always kind. But this last thing that I want to say about bundles before we move on is this really, really special theorem from Pillai. I think it's from 1961. And it's saying something about the morphisms of principal G bundles. So if you have a morphism of principal G bundles, then it's a bit of a miracle that the domain bundle or the total space of the domain bundle E is actually always G equivariantly isomorphic to the pullback bundle G star of F. And so, okay, so one thing that I didn't say that maybe I ought to before is that pullbacks enjoy a very, very nice universal property, right, in the category of topological spaces. In fact, I think that pullbacks are a general thing in any category, and this is some of the reason for the name. But so in fact, it's always the case that for a pullback, you can define this map H, which kind of supports and says, okay, well, if you've got this morphism from EPB, then somehow you can always get this intermediate map going to the pullback G star of F. What Pillai's theorem is actually telling us is, okay, well, if it happens that F is G equivariantly isomorphic, and if it happens that the bundles E and P are principal G bundles, then this is enough information for us to know not only is there a continuous map H, but H is in fact a G equivariant homeomorphism. So this is a huge amount of rigidity that we have for these particular kinds of bundles. And we're going to see this come into play fairly critically a little bit later.
So you're telling us that the pullback is actually a pullback.
The pullback is actually a pullback, yes. But now I'm going to go ahead and move on.
Sorry, if I could comment. So this theorem, in fact, is a little bit more stronger because it says that every J equivariant map between principal vector bundles,
Y vector.
Sorry, principal bundles. Okay, is a pullback.
Is the pullback? Yeah, that's another way to interpret. Yeah, you're right.
In particular, if you have the same base, then every such a morphism is an isomorphism of principal G bundles.
Correct.
In particular, these principal G bundles over a fixed base form a groupoid, for instance.
Yeah. Excellent. Excellent. So yeah, this is quite a strong, quite a special result that we're going to see come into critical play. But now let's actually introduce some of the topics, some of the subjects that we're going to be talking about, these topological quivers. We can kind of play with them a little bit and see what's going on. So now a topological quiver is going to be an ensemble. It's going to consist of 5 elements, E0 and E1. These are going to be locally compact Hausdorff, and I neglected to mention second countable topological spaces. And we're going to have 2 continuous maps, R and S, going from E1 to E0. And then what else do we insist? We insist that S is actually an open surjection. And we insist that there's also an S system of measures. Okay.
By the way, in a principal bundle, this bundle map is always an open surjection.
Yes, which is very good. So topological quivers, maybe if you're familiar with graph algebras or directed graphs, then this is exactly a lot of the data that we're familiar with. And I've even packaged it in such a way that it appears very similar, right? We've got this map R and this map S, the range map and the source map is how they're usually called. And in fact, throughout this talk, I'm going to talk about E0 being the vertex space and E1 being the edge space by analogy with what we actually see in the directed graph setting. And in particular, directed graphs are especially a case of this, where we insist that our topological spaces are discrete, and well, then there's no continuity assumptions that we need to apply to the range and the source maps.
Not quite, because you assume by this subjectivity that there are no sinks.
Okay, yeah, you're right. There's a point here. Yeah. So, well, but in fact, there's this technique where you can remove sinks from a directed graph anyway, right? By adding tails to the directed graph. But this is maybe a small nuance that is worth taking a little bit more care with in the appropriate setting.
Yeah, but you cannot do it without changing your algebra.
Yeah, fair enough. So
Sorry, I have a question.
All right, go ahead.
If you are adding to the definition of a topological quiver this system of measures, why do you call it still topological? Because it's counting more than the quiver object in the category of topological spaces. There's some extra structure. The choice of this system of measures.
Yeah, sure, that's true.
It's a little bit more than topology.
Yeah, well, I'm going to reflect on that for a little bit. I'm going to move on while I think. So I've got a couple of examples that I've produced here. Okay, so we've seen a bit of an example of a rectangle before with the system of measures. Now I've got just a square, and so I'm trying to describe what's going on with it. Okay, so this square has a projection onto the first coordinate, which I'm calling the source map, and a projection onto the second coordinate, which is the range map. And so you can also see how the source and the range maps are described, and in particular, what should this system of measures be? Well, it should be, just like we had before, one of these vertical lines, which passes through these things. And in particular, this actually shows us something that about how topological quivers generalize some of the structures that have already been introduced, like, say, Katsura's topological graphs. Katsura assumes that S is actually a local homeomorphism. And a consequence of this is that the fibers over the preimage are always discrete, and so a measure doesn't need to appear. But a topological quiver is more general in the sense that, now our fibers are allowed to have some kind of topological data, some type of, something really, I'm going to say this word diffuse about them. This is allowed. And so really this extra bit of data is different. This is something that's new and more general. On the other hand, these topological quivers are flexible enough that they do cover all of the examples of, say, directed graphs. But for the sake of how this talk is going to proceed a little bit further, I want to think about directed graphs a little bit in a funny way, a way that's maybe unintuitive compared to how we commonly see them. So, for example, we've got the single point and a single loop directed graph. And how I kind of want to think about this is, instead of being a single point for the vertex space, I want to think about it as being 2 points, one being the source, one being that point viewed as the source, and one is as that point being viewed as the range. And then what we end up doing is we end up identifying these two things at the very end so that we get this commonly defined notion of a directed graph. But the splitting is going to help us see a little bit, with a little bit of context, how some of the operator algebraic analogs are going to come about. And so for that matter, I've also included this example with this other famous directed graph in the operator algebra setting, where, okay, once again, now we've got two vertices. And so what we're going to do is we're going to split them up and say, okay, one line, the top line here, is given by those vertices viewed as sources, and then the bottom line is then viewed as targets, and then we're going to go ahead and identify them to be able to think about them the way that we usually think about a directed graph. Okay, so great, we've got topological quivers. Now I'm going to introduce this construction that I invented, I guess, of course, with a lot of history behind it. This is the skew product of a topological quiver. So what you do is you start with a cocycle, which is just the name for a continuous map, which goes from the edge space into a group. And what you do for the skew product is you define a new bunch of data. Namely, you take your original topological spaces E0 and E1, and you take the Cartesian product with G. Then we are going to need to find new range and source maps, and then a new system of measures as well, in such a way that, we get all of the information that we needed to actually get a topological quiver. The theorem here is, yes, it is in fact a topological quiver, but we need to arrange for things in the right way. And just for the sake of context...
I'm sorry, but who is this guy who proved it? Another guy.
I'm sorry?
Who is this guy who proved that theorem?
Oh, that's me.
No, no, it's all in single letter.
Oh, yeah, you caught me. AMS ref
1-0 for us.
Okay, so something that I'll point out is this is the technical reason why we insist that G is a second countable locally compact group, is simply because, when we define the skew product, we've already insisted that the topological spaces involved in the topological quiver need to be second countable as well. So this is the reason why G has to have this restriction. I speculate that, with enough of a refinement of the definition, you might be able to get similar results for G not second countable as well. But this is something for a later time. Anyway, what do we need to do to actually get a skew product? Well, what I'd like
I have a question. So the group G itself could be understood as a quiver with only one object and all elements of G corresponding to loops.
Kind of like Hawaiian earring, right? Oh, infinity,
Yeah.
of course.
So is there some operation on quivers which, restricted to this case, will give you this Skew product? Can you extend your definition of the Skew product with some operation on quivers?
I'm not quite sure. To be honest, so some of the idea of one thing that I want to point out just in general is that loops are sort of, in an appropriate sense, poorly behaved from the context, even from the context of directed graphs, right? These quickly lead to like infinite dimensional phenomena and these kinds of things. That while interesting, are maybe, I find them not to be the most fruitful way to be studying these things, at least once you go into the operator algebraic setting. Kind of like the idea that, a groupoid is actually an example of a topological quiver as well. Right, because even if you have these Haar systems of measures, but somehow the constructions which are viewed as the constructions which are viewed as appropriate for topological quivers are less structured, right? Instead of viewing like the continuous compactly supported functions on a groupoid and then taking some appropriate completion, doing something that's somehow a lot bigger. So this seems to be, in my perspective, not the right picture to look at.
I also have a question. I also have a question, because it looks to me, this, construction, this product and so on, it looks to me like a proof of Rayburn-Szymański, the famous proof which computes K-theory out of a graph. It really looks to me that there was similar technology used, and he was kind of unwinding the graph by taking condition products, and then they were proving, aha, now we have something which is Morita equivalent to the original graph algebra. Do you know what I'm talking about? The proof of Rayburn-Szymański?
No, so I don't. So I know enough to understand that the K-theory of a graph algebra is connected to its adjacency matrix, but I haven't looked at all at the proof of this. But it seems to me that this is the right thing to do, right? You can kind of extend by a Cartesian product and kind of unwind things. And actually, I think there might be some pictures which give a little bit of more motivation to this.
So have a look at it. Have a look at this proof. To see if you can somehow connect more dots. But please don't say it's connected. I mean, it's determined. It's more than connected. It's just determined.
Yeah, sure.
But it has all that of graph sister algebras, but you have a K-theory served on a plate.
Right. So, okay. So just to keep everybody on the same page. So what do we do, right? So we've got a Cartesian product of E0 and E1 by G. And we define the source and the range maps in this particular way. So for the source map, we're actually going to do nothing. We're going to say, okay, well, if you give me a pair given by an edge element and a group element, all I'm going to do is I'm going to take the source of that edge and the original group element, I'm going to do nothing to it. This is a very boring map, very well behaved. However, the range map, we're going to do something a little bit more exotic. If we take a pair E and G, we're going to take the range of E in the first coordinate, and we're going to keep that element G floating around, but we're actually going to multiply by this group element, which is naturally associated to the group E.
Sorry, so what is it, K or kappa? I'm confused because cocycle in the first line is kappa and then it's K. It should be kappa.
Yes, it should be kappa. You're right. Very discerning. Yeah, this should be a kappa here. Okay, so the theorem is that in fact.
Sorry, I must have a question.
Yeah.
Here, because you are calling this map from E1 to G a cocycle, but you don't have a composition in E1.
Yeah, that's true. So somehow, this name of a cocycle is this is a relic from the from the history of skew products in other contexts.
So it's simply a map.
I frankly, I don't see I don't myself see the relation between cocycles in like the homological sense and how it's defined here. But this is for historical reasons. This is we're calling this a cocycle.
Yes, but in this case, it's simply a map from E1 to G.
I assume it's a continuous map.
A continuous map.
Yes, it's a continuous map.
All maps are continuous here.
Yes.
Okay, good.
All maps were created equal.
Okay, and so we can see a couple of at least discrete examples of how the skew product actually works. If you start with this cyan map, right, or this top or this directed graph which had this cyan arrow from U, then well, what we can do is we can say let's assign to that single edge the generator of the integers, right? And then we can see that we actually generate this infinite directed graph where each vertex emits and receives exactly one vertex. On the other hand, to see some of the flexibility of this skew product construction, I've got two examples of how to extend a skew product from this black map with two vertices into other ones. The first one says, okay, well, let's take the group Z2 and let's go ahead and map both of the edges to the identity of that group. Well, if we're mapping everything to the identity, then, okay, all we've done is we've taken a Cartesian product and there's no actual skewing going on. There's no actual skew that happens. However, if instead we say, well, we're going to let the edge going from V to W, we're going to map that to the identity. But the self loop from V to itself, we're going to go ahead and let that be perturbed by the generator of Z2. And then we see that we get this more interesting phenomenon occurring in this graph all the way to the right. And in a similar way, once you have topological spaces or topological groups, then you can kind of see that there's you're extending by the group, right? By a Cartesian product by the group. And this is really kind of the principle of the thing. You're allowing yourself to shift as you move along to different hyperplanes is the word that I guess I'll use.
Mm-hmm.
Okay, so a skew product. Now, what's the main theorem, at least for this topological set? The main theorem goes as follows. First of all, there is a principal group action on the skew product topological quiver. And moreover, the quotient by this principal action recovers the original quiver that you started with if you go by this construction. And conversely, if you have a principal action of a group on any topological quiver R, and you know that this quotient map for the vertex, for the vertices is actually a trivial bundle, then we can identify R as a skew product topological quiver. So let's briefly go through this. The whole idea for having a group action on the topological quiver is the following. Well, we're going to, Piotr, you're going to be very happy. I'm going to allow us to act on the right. So what we see here is that if we allow the right action on the second factor of the Cartesian product, that we have actions on each of the vertex and the edge spaces. And moreover, according to the definition of the source and the range maps, we see that these source and range maps are actually equivariant for this G action as well. Furthermore, this lambda system of measures, you might have thought that that we would have to introduce the Haar measure somewhere, but no, this is actually not the case at all, because we view these points G as being vertices. So we only need to know what happens at a single vertex, which is a pair. So the group structure doesn't really play a role. We're thinking of this spatially at the moment. And it turns out that as you transition among different G elements, that you get the same lambda measure, right? So as you move along, you're measuring the same fibers the same way even as you translate to different hyperplanes. And so then it becomes abundantly clear that if you take the skew product and you take the quotient by this G action, that you actually recover the original topological quiver Q. The more interesting thing, I think, is that if you have any topological quiver that admits a principal G action such that the quotient map just for the vertex space is trivial, then we can actually identify R as a skew product follows this diagram that I'm seeing here. So what do? Well, we've got these maps S hat and R hat, which go from F1. F1 is going to be the edge space of R, and F0 is going to be the vertex space. And well, lemma, the quotient by a principal G action of on a topological quiver recovers a topological quiver as well. So we end up getting a picture that looks like this, right? Over here we had the pullbacks, but if we know that the quotient map is trivial, then we can actually recognize that exactly these pullbacks are given by keeping the fibers that we had before, right? This is exactly what the pullback does. It keeps the fibers that we had. Since we know that the fibers are trivial, this space is actually E1 cross G. Okay, so good. Now we're beginning to see how we can view R as a topological quiver. F0 is just a copy of E0 by G, and E1 by G is, well, exactly the edge space for a skew product as well, right? Since this since this is just a projection onto the second coordinate after just a little bit of squinting, then we see, okay, well, this is maybe the first part of where we want to see our skew product topological quiver. The only hard part is seeing what the range map does. But fortunately, by Pele's theorem, we know that we have homeomorphisms here going from that sigma and rho are both homeomorphisms, right? Going from F1 into E1 by G. So our candidate for that range map is going to be, okay, well, we're going to compose by sigma inverse, and we're going to post-compose by rho afterwards. And then after taking the same projection, getting from E1 by G to F0, which is isomorphic to E0 cross G, then we can see that, oh, this should be a topological quiver. The only concern is, okay, well, the promise is that there's some kind of a co-cycle floating around that we're interested in. Okay. Well,
sorry, Lucas, I'm a bit confused. What are your assumptions about the script R? All I can see is that it's a G space, nothing more.
Oh, sorry. Yeah, R is supposed to be some topological quiver.
So let R be a topological quiver with an action of G on what? What is
on the topological quiver? And by this I mean, maybe I was being a little bit slick here. By this I mean we've got principal actions on the edge space and the vertex space.
Principal
Actions on the edge and vertex space. And also the range and the source maps are G equivariant for these.
Okay, and then Q, of course, I mean, is a part of the structure of R.
And then Q is, yes.
I mean, lowercase q, right?
Yeah, this Q is part of the structure of R. Well, Q is really because
no, it's a quotient. So, but F0 is a vertex space for R.
Yes, exactly.
Yes.
This.
So I mean, you skipped a lot in this
R0 and so on.
Yeah. There's. I could fill up a whole page. I could fill up a whole page with just the statement if you preferred, but there's a lot going on. That's for sure. But in principle, this all breaks down to give us, well, where was I? That we have this map sigma that we can take the inverse of because of Pele's theorem. This is a homeomorphism, G equivariant even. Likewise with rho, and so we can take their composition, which is just a map from E1 by G to E1 by G. So what do you do? We can describe this as a map psi, which takes as inputs EG and outputs an edge E1, and another map phi, which takes inputs E and G and outputs a group element. But the way that this diagram is constructed should convince you that, in fact, this map psi is trivial. It does nothing. Because, well, on one hand, the projection onto the first coordinate needs to commute with sigma inverse compose rho, compose the projection onto the first coordinate. So there's no actual contribution from psi here. But just to be abundantly clear, in this last moment, I'm just trying to say, oh, there's an actual co-cycle that you can extract. So you can say, oh, in fact, once you take the quotient topological quiver, then we can actually find a cocycle which we can reconstitute R and see that we have a homeomorphism here. So we're just looking for a map which goes from E1 to the groups, or to the group G. That's all that we need. And my proposal for you is that this map kappa is going to be just this phi map where we replace G with the identity. Just
by equivariance, of course.
Yeah, because we have equivariance, exactly. We have equivariance of sigma, therefore sigma inverse, and we have equivariance of rho as well. And so really this map is completely determined by what it does to a single edge map, or to a single edge. And this is how we actually recover this cocycle. So
I have a question.
Yeah.
I have a question about your assumption of principality.
okay,
Is this action of G principal on the level of F0, or is it principal on the level of F0 and F1?
He said F0 and F1.
Both.
on both. Yeah, it's principal on
Okay.
both.
He's a very principled person.
Okay.
At least
you
this
stick to your principles.
Yeah, so this is how we end up getting a topological quiver R. Piotr, when do we finish? I want to make sure that I'm being
You have 40 minutes without, 39 minutes.
Okay, excellent. Good. So I think that we're doing pretty good for time.
Yeah.
Okay, so this has been a lot of topological conversation that we've had, but of course we're in a non-commutative geometry talk. So I'd like to at some point bring in some operator algebras and some things concerning this. So if it's okay with everybody, what I'd like to do is I'd like to push a couple of things through the Gelfand functor to motivate the notion of a coaction, which we're going to see coming into play just a little bit later. So to start, right, we've been talking about actions of a group on a topological space. And so the idea behind this is somehow the action is supposed to, in some appropriate way, keep track of the group multiplication, right? If we choose to act by a group element on a topological space and then act by another one to get a single point in space, the assumptions of an action say that this better be the same thing as if we take two group elements, we multiply them together using the multiplication from the group map, and then we apply the action to this thing here, right? Well, these are all continuous maps from a topological space. So instead, we can go ahead and ask, okay, so what's happening in the commutative C-star algebra setting, right? It's a contravariant functor, and so instead of ending with a single point x, we're starting with a continuous function on C0 of x. And what can we do? We can take the functorial, well, we can take the image under the functor of the action map, and we can apply it in two ways. Well, that's not true. We can apply it exactly once. We can apply it and get and end up with something in, say, the multipliers of the tensor product of C0 of x with C0 of g. But then once we're here, we have two things that we can do. We can look at this left leg of this tensor product and say, oh, well, I'd like to apply the action another time, but I'd like to apply that action only to this left leg. And that's going to give us something that's in here, C0 of x with the tensor double of C0 of g. And then on the other hand, we can look at our action, and we can say, oh, well, hold on, I have this really beautiful multiplication map that took two group elements and made one and produced one. That means that in the commutative C-star algebra case, we have one map that takes a single continuous function on G and gives you a continuous function on the tensor double. And the assertion for an action in the group setting, it gets translated exactly into this notion here that we have this kind of a commutative diagram by exact analogy with what we had before. Okay. So this ends up being a way that we can interpret an action in general of a group on a non-commutative C-star algebra as well, right? You define an action to be, a non-degenerate star homomorphism into the multipliers of A tensor C-star of G. And we have two different ways that we can apply it, right? Once again, we can ask, okay, well, what happens if we just look at the left leg of this tensor product and apply that action another time? And compare that against, well, we've got this C-star algebra C0 of G, and we've got this nice multiplication, or this nice star homomorphism here, so we can apply it here. And in general, an action can be described using a diagram much like this.
Yes, like they're using the notation if alpha means a star homomorphism, because then what goes down on the right-hand side is not alpha tensor ID, but the extension of alpha, which is possible due to the non-degeneracy assumption.
Yes, that's exactly, yeah. Yeah, being more careful to be sure. Yes, that's exactly true.
And you switch from the left to the right.
And I've also managed to switch from the left to the right, I think, as well. Yeah.
Yeah. Very good.
Now of course, what do we like to do with C-star algebras in general is we like to represent them. What do we like to do with actions? We like to represent them as well. And so what I've included here is another picture, which gives us a description of what a covariant representation of this action should ought to be. Well, a covariant representation of an action should include, well, a representation of the C-star algebra A, that's what I'm describing by pi, into the multipliers of some C-star algebra B. And let's say this is a non-degenerate homomorphism, just to be safe. And we also include a representation of the group, which I'm communicating as as a star homomorphism from the C-star algebra, C star of G, into the multipliers of the C-star algebra B. And what we would like is to see that the way that this map pi and this map U embed into the multipliers of B is in a way that's somehow compatible with the action structure that we had from before. And the way that we do that, that we would like that to happen, our dream would be if we could get it to be by some kind of conjugation, right? Some conjugation which is associated to how this unitary embeds in B, and that would be great. So what this tells us is, okay, so maybe we don't have an action of this group on all of B, but at least if we restrict our attention to the action or to the image of A, then what this diagram wants to communicate, what I want this diagram to communicate anyway, is that the action is exactly captured by a conjugation at least restricted to the image of pi.
So assume A be a commutative C-star algebras, and assume
no.
even everything is unital. So we are compact. So what would this picture mean? How would you draw this diagram if A were a unital commutative C-star algebras? How would you draw this diagram in terms of compact Hausdorff spaces?
Oh, that's an interesting question. I haven't thought enough about this actually. I'm gonna have to ponder that, Pio, but I don't have an answer for you off the cuff.
Okay, homework.
Yeah, good. Okay, so now what I'd like to do is I'd like to use these pictures that we have here as a motivation for what should happen in the context of a coaction. Because, and the motivation really comes from the following. It comes from the idea that, okay, well, in the classical setting, if we have an abelian group, then the group C-star algebra of an abelian group is commutative. So it's homeomorphic to the continuous functions on some locally compact Hausdorff space. Good, it's going to be different, right? In particular, if your group is discrete, then the C-star algebra of G is going to be compact, right? And vice versa. This is fairly well known. Now, what we do by analogy in operator algebra land is we're not concerned with whether or not our operator algebras are commutative. So what we're going to end up doing is we're going to say, okay, well, what I'd like to do is I'd like to replace all this talk about G with G hat, right? With the dual of G. But even when this doesn't exist. And it turns out that the right way to do this is to take all of your instances of C0 of G and just replace them with C star of G. And take all of your instances of C star of G and just replace them with C0 of G. And this ends up being capturing kind of the notion of a coaction, which has a very well understood duality theory with the theory of actions in general. And so, okay. So this is pretty much all the same information that we had before, except for, like I said, I'm just replacing all the C0 of G with C star of G. And now I'm replacing this map alpha, which we think of as an action, with this map delta, which is the common notation for a coaction. Okay, so what's maybe the example that I want to give to say, okay, these coactions are a worthy thing to give a little bit of investigation to? And maybe this is a little bit suggestive too. The idea is, okay, suppose that we have a topological space and we've got a continuous map which goes from X into the group, into a group G, another one of these co-cycles, if you'll pardon me. So then what this does is induces in the C-star algebra level a coaction from C0 of x into the multipliers of C0 of x tensored against C star of G. How does it do it? Well, we can identify this multiplier algebra as the continuous bounded functions from x into the multipliers of C star of G. And in that case, we can actually say, okay, well, it's enough for me to say dk of f, what does it do to a single point? Because now we're thinking about a map from x into some C-star algebra.
Okay, but wait, I'm confused. Delta k of f, is it the multipliers?
Delta k of x, delta k is a map from C0 of x.
Yeah, but once we evaluate it on a continuous vanishing and infinity function on x, you land in multipliers. And now why is this guy in the multiply? Aha, you view it, okay, you view it as a function from x to C star of G.
A bounded function.
And a bounded function from C star of, from x to C star of G, okay.
To the, and even to the multipliers of
Okay,
C star
yes.
of G.
Yes, you're right, okay.
And then this will all start to make sense. So what do? We just take that point x and we evaluate our continuous function at x. So that gives us a scalar.
Yes.
And then what else do? We also
so
take,
why bother with a tensor product if it's a scalar?
to keep the symmetry of the picture?
No, it should be
No, because
multiplication by a number.
no, it's not symmetry because in the picture you have a tensor product and algebra, so it's a tensor product. Once you evaluate, you go from your algebra to complex numbers. Nobody writes a map like this, you know. I mean, you don't write the field tensor in algebra, of course, if you.
Okay, well, sure.
I mean, it's confusing. I can tell you why it's confusing because then I immediately assume that f of x is not a scalar.
It's a number.
But it is
If
just
I see a tensor product, I assume, okay, so it's not a scalar, that's why he had to write the tensor product.
Yeah, well, okay, well, I guess in this way I get to keep the analogy here and suppress the idea that I'm that I'm, you know, evoking this homeomorphism. But this is semantics, right?
Yeah.
In any event, this nice example of a coaction is given by some kind of a, you know, like a cocycle, right? And so once again, by analogy, we also have, you know, the notion of a covariant representation, where we can take our C-star algebra A, and we can take the C0 function, the continuous functions on G, and we can embed them both in the multipliers of some C-star algebra B. And we'd like to have it all be compatible in such a way that this diagram ends up commuting, right? If you coact and then represent, that better be the same as if you represent and then coact by some kind of like conjugation. And in fact, it is a conjugation type map that we have here, but I'm suppressing notation to keep us, well, at least a little bit more comfortable for this context. This isn't the point of the talk anyway. Okay, so maybe this is enough about this, and we can actually get back to the objects of study, these topological quivers that we had started with. That's not true. One other thing that I want to talk about first is the idea that, well, once again, if you have an action of a group on a C-star algebra, then you can define a cross product, right? Well, it turns out that you can do the same thing with a coaction, and it has the same properties, right? The point of a cross product is it's a C-star algebra which somehow captures all of the representation theory of the action. Well, a coaction does exactly the same thing, or a coaction cross product does exactly the same thing. It's a single C-star algebra, which somehow captures all of the representation theory of a coaction in this following sense, that if you ever have a representation, a covariant representation for your coaction in some C-star algebra B, then automatically you have a star homomorphism, which goes from the cross product, the coaction cross product, into the C-star algebra. So this cross product captures all of the information of covariant representations for a coaction. And that's what I want to leave us with before we move on. Okay, so now...
Sorry, I have a question. So, yeah, what's the relation between this cross product with this data containing this, let's say, cocycle?
In this particular example here.
Yes.
There's a good answer to this.
In which sense it is yeah.
Yeah, so in fact, it turns out that this cross product is going to be some kind of a, it's going to be maybe I'll say this.
Because delta K is not a coaction.
I'm sorry?
Delta K is not an action.
No, it's a coaction.
It's not a coaction.
Delta K is a coaction. That's what I'm trying to say.
Because K was a continuous map from X to G.
No, wait, delta K is a
but look what delta K
Listen.
does. Delta K maps us into C
map.
star of G by
Yes.
asking what's the embedding, or how does that group element embed into C star of G?
Yes, but how? Okay, above you have a diagram which is an axiom of a coaction.
yes.
Below you have delta K. But since you don't have any kind of, what do you have here? Do you have an action, coaction?
It's a delta K is a coaction.
And he tacitly assumes that we know how to go from C star of G to C star of G to C star of G, right?
Yeah.
Yeah, I'm implicitly assuming that. Again, this is not exactly the subject of this talk. It's related, of course, but
Be related, but
okay, well, let's not belabor this, if it's all the same. To answer your to answer your original question, actually the idea is that this, in the case of this coaction delta K, it's going to turn out that the cross product, the coaction cross product, is going to be somehow related to.
So you are assuming that K or kappa is such that it is a coaction.
That the induced delta K is a coaction.
The delta K is a coaction.
Yeah, delta K is a coaction. This is just a continuous map from a topological space into a group G. A continuous.
No. It's a such continuous map that induces this coaction, because arbitrary map from X to G in principle doesn't induce any kind of a coaction.
Lucas, the point is that if you take just an arbitrary K from X to G, which is merely continuous, okay?
Mm-hmm.
And then you put up this definition of delta K, we find it hard to believe that this diagram, which is at the top, is commutative. However, we are very happy with a situation in which you say, aha, so let's take K continues from X to G such that delta K given by this formula makes the above diagram commutative.
And then it would justify the name cosine. Yeah?
Okay.
We
Okay. Very good.
do you concur with us?
I think so.
Okay. Thank you.
Of course. So, so now let's move on. So let's try and see how we can get the data from a topological quiver into the non-commutative context. So what I'm going to do is I'm going to take A to be the C-star algebra, which is just the continuous functions on the vertex space. I'm going to take X0 to be the continuous compactly supported functions on E1. And what I'd like to do is I'd like to build a C-star correspondence. So what is this? This is a Hilbert, a right Hilbert A module. What's that? So that means that it's a module over the C-star algebra A, which admits an inner product and together with a right action of A. And furthermore, I'd like there to be some appropriate left action of A on this Hilbert A module as well. And well, best of all is that I'd actually like all of this information to capture somehow the data of a topological quiver. And so I've got this, mathematics written here that if you take a function in C's, a function supported on the vertices and a compactly supported function supported on the edges, well, this is how I'd like to arrange this data. If you take the product on the right and evaluate at some edge E, what you do is you evaluate C on the edge and you evaluate F at the source of the edge. On the other hand, if you multiply on the right by F on C, then you precompose with the range map. You multiply against the ranges. As for the inner product, this is where we see this system of measures coming into play, is that if we take two elements, eta and xi, then what can we do is, well, we can multiply them together, taking the complex conjugate of one, and then we can integrate that new function, which is still a compactly supported function, against, you know, your favorite measure coming from the system of measures. And the continuity of the system of measures ensures that you still end up in C0 of E0 in this in the coefficient algebra that we begin with. Then once you, if you believe all of this, then you can take X naught and you can complete it with a norm, which is coming from this inner product structure together with the norm from A, and call that our Hilbert module. And this is how you get the Quiver correspondence. This is the idea.
So please correct me if I'm wrong. I mean, the first two formulas before the integral, they just give us a bimodule structure of X naught over A, right?
Yes.
And then better still, you turn it into a Hilbert module.
That's right. Yeah, the inner product turns it into an inner product, a right inner product module, and then the completion turns it into a Hilbert one. That's exactly correct.
So just let's be discrete for a second. Imagine that I have the usual graph, not topological one.
Okay.
So what would be, so I have these X naught, these are finitely supported functions on my space of arrows.
Yeah.
And what is an X?
What is a...
Well, after you complete it, so.
what? Oh, okay. So this will be interesting. So it'll actually be, this will be a Hilbert bundle, where a Hilbert bundle over the vertex space, whose if you give me a vertex, the Hilbert space over that vertex is is the dimension equal to the number of edges which are emitted from that vertex.
Okay.
And I've got some pictures to support this as well.
Okay.
So once more, maybe the most nebulous thing is this inner product business that's going on. So I've included, you know, yet another picture to try and illustrate what's going on another time. Okay, so you take two functions which are, you know, supported in this space. You take the complex conjugate of one, and then you integrate against all these individual fibers, and that constitutes a function down here, which will still be compactly supported, in fact, not just C0. And so this is what the inner product is actually doing. Now, as for the left and right actions, this is why I had asked that before we kind of suspend our usual notion of how a directed graph ought to look and try and think of it in two pieces, in a emitting space and a targeting space. Because then I can take this picture and say, okay, well, if I want to act on the right-hand side, then I'm going to be somehow doing something to the sources. And so if I had some function, which I'm describing by all of these colors again, then I can see, okay, well, the arrangement of the data has me going purple, blue, green, orange. And in this
it's lime, it's not green. It's lime.
Okay, lime it is. And you can see that at least in this particular section, that red doesn't get described at all. But meanwhile, if we apply on the left-hand side instead, we see that we get different behavior. Red is described, and the purple is the color that isn't here. So this is all of this is meant to convince you that this Hilbert module structure associated to a quiver really somehow is capturing in the discrete case, the combinatorial data, but also the topological data, which is kind of baked into everything. Okay. So now we can talk a little bit about correspondence homomorphisms, which all I really want to say about them is a correspondence homomorphism's job is to take two correspondences and to see how much of the data from the domain we can represent in the codomain. So this means the right and left actions need to be compatible. In particular, pi needs to be a star homomorphism, and psi needs to be a linear map between x and y. And it has to obey inner products, and it has to obey left and right actions in a way that you can arrange and make perfect sense of. A particular example of a correspondence homomorphism is the Toeplitz representation, where, okay, you have some native correspondence that you're interested in XA, and we want to represent it in just a C-star algebra B, because it turns out that a C-star algebra is a perfect first example of a C-star correspondence. The right action is by multiplication on the right, left action is by multiplication on the left, and the inner product is B valued, and it It's given by you take you take two elements and you multiply the adjoint of one against the other. So this is a perfect example of a C star correspondence over B. And a Toeplitz representation says, okay, well, let's take this correspondence that we're interested in, XA, and let's represent it as operators. So for us, we're interested in, well, okay, so let's start with this. Why would we want to do that? Well, because then we could ask, okay, how are all these operators interacting together, right? We can ask, what is the closure of the image of this correspondence homomorphism in a C star algebra, say?
Sorry, Lucas, I'm confused. How can it have psi, pi going simultaneously from XA to YB and to B alone?
No, it's a BB. It should be, of course.
You mean B?
Yeah. I'm doing the common thing where we can think of B as being a correspondence over itself. So I'm instead of writing BB in parentheses, I'm just taking B itself.
X goes to B and A goes to B.
Yeah, and X is only required to be a linear map. Pi is required to be a star homomorphism, but they all need to be compatible with the correspondence structures is the idea.
Okay, so you take as your Y B itself.
Yes, exactly.
Okay. I would much more prefer a BB.
Okay. So now what I'm in particular going to be interested in is the Kunz-Pimsner algebra, which is associated to a correspondence. So certainly I don't want to get into the details of this either. There's a certain class of Toeplitz representations which are particularly well behaved. These are called Kunz-Pimsner covariant. And so the Kunz-Pimsner algebra is supposed to be the universal C star algebra for Kunz-Pimsner covariant representations in a C star algebra B. So the idea is that in this diagram, our Kunz-Pimsner algebra admits a correspondence homomorphism from XA into this C star algebra, which I'm denoting by KX and KA. And the thing is, if you ever have another Kunz-Pimsner covariant representation, which I'm calling by psi and pi in a C star algebra B, we automatically generate a C star or a star homomorphism from the Kunz-Pimsner algebra into this representing algebra B. That's the idea. Now, for a correspondence associated to a topological quiver, we're going to abbreviate and get rid of a bunch of this notation just by saying, okay, well, this is the C star algebra that we're talking about when we talk about the C star algebra of a topological quiver. It's C star of Q. And so in particular, C star of Q captures all of the correspondence data, which is coming from the correspondence which is associated to the topological quiver. That's the principle.
Do you mean that you can reconstruct your correspondence from this Kunz-Pimsner algebra?
Ooh, do I mean to say that? No, I don't think that that's the case.
It would be too far.
But what I mean to say is that this Kunz-Pimsner algebra captures as operators, at least. If you have any representation by operators of your correspondence, then this, well, which is Kunz-Pimsner covariant, then this Kunz-Pimsner algebra will capture it. There's another algebra which is actually larger. It's the Toeplitz algebra, and this Kunz-Pimsner algebra is a quotient of that. But largely, it's understood that the Toeplitz algebra is too big for us to manage very, very well. So people commonly will look at this quotient algebra instead because it's very, very well behaved. It's also co-universal in the sense that I don't want to speak out of turn. I don't have the words to put it together right now. But this is an appropriately small C star algebra, which still captures the Toeplitz, all the Toeplitz representations of your correspondence.
So this means that this algebra is defined in terms of some universal property.
Yes. Yeah. It also admits a. Is this true? Someone was just telling me that this admits a representation on a Fock space, but I'm not 100% sure that that's true. So I'd have to see it for myself. But usually it's taken that this Kunz-Pimsner algebra is defined by a universal property. Yes. Okay, so a little bit of more information about correspondences is there's a nice extension, kind of like how multiplier algebras exist for C star algebra. There's also a multiplier correspondence. It's given by exactly, well, you take the adjointable operators with inputs from B and outputs in Y. And in particular, this multiplier correspondence admits an embedding of Y inside of it. It's given by, okay, well, you give me an element Y, can I view it as an adjointable operator from B to Y? Well, you just view it as itself, and then whenever you take B as an input, you just do right multiplication against it, and then you're going to end up with something in Y. So this multiplier correspondence is it's newish. I think that it was really studied well only in 2013, and in this particular context of this theorem that I'm about to state. But here's the principle: is that once you have this multiplier correspondence, you can also describe the idea of a Kunz-Pimsner covariant correspondence homomorphism. This is genuinely new. People had studied Kunz-Pimsner covariant Toeplitz representations where the correspondence homomorphism was into a C-star algebra. This is the first time that this had been studied, I think, in the... And maybe it isn't the first time, but certainly it's the most general time that this has been studied, this Kunz-Pimsner covariance for a homomorphism. And the whole punchline is that there's some kind of appropriate functoriality for Kunz-Pimsner covariant maps, which essentially says the punchline of this theorem, that if you have a covariant correspondence homomorphism from XA into the multipliers of Y and the multipliers of B, then you end up with a unique star homomorphism, which goes from the Kunz-Pimsner algebra, which is associated to X, into the multipliers of the Kunz-Pimsner algebra associated to Y. And in fact, it's even stronger. If pi is injective, then this map is also injective as well. So there's a nice amount of rigidity that's going on with these Kunz-Pimsner covariant correspondence homomorphisms.
Another sanity check, if I may. So imagine that my correspondence comes from a graph.
Okay.
And then what would be this morphism, psi pi, between correspondences in terms of a graph, of graphs?
Okay, in terms of a graph, let's see. Okay, so remember we had this construction that this closure ended up being a Hilbert bundle, right?
Mm-hmm.
Okay, so this map pi should be a star homomorphism from C0 of the vertices to Z0 of the vertices of a different graph.
Mm-hmm.
Yes. And
okay.
This map psi, I think that this should embed any one of these Hilberts, any one of the fibers of this Hilbert bundle into an appropriate Hilbert bundle on the other graph. I think that that's what that should be.
So from the point of view of a category of graphs, this would be a contravariant function.
I think so.
Okay.
I think so.
Okay, thank you.
Yeah. Okay, so we have this commutative diagram. How does this apply to us? Well, remember, we've been talking about the C-star algebra, which is associated to a directed graph. And we've also been talking about the idea of a skew product for a topological quiver. So what I'm going to do now is I'm going to put XA as the correspondence which is associated to a topological quiver Q. This should be a MathCal, sorry. And YB should be the correspondence associated to the skew product topological quiver. And I have shown that there's a star homomorphism, which I'm calling capital pi, and it goes from the C-star algebra of the topological quiver, right? This is the Kunz-Pimsner algebra, to the multipliers of the Kunz-Pimsner algebra associated to the skew product instead. How does this go? Well, the punchline is that it turns out that these quotient maps that we have for the skew product are going to induce a Kunz-Pimsner covariant correspondence homomorphism going from XA to the multipliers of Y and the multipliers of B, the multiplier correspondence spoken generally. This actually takes a significant amount of work to get this done. There's a lot of details to check, but really the takeaway I think from this theorem is that, wow, it turns out that our dreams do come true. That quotient, that just pre-composition with the quotient map is exactly what we need in order to make everything work in this setting. That's really the idea that I want to take away from here.
I have a question. Could you come back? I have a question about this right-hand side in your theorem.
In my theorem, okay?
Yeah, C star of Q cross over K with G seems something like some operation on sister algebra of Q, sister algebra of G, and twisted by delta K. Is it
No.
the same?
Oh, okay. Well, let's
That's a good question.
hold this question. But so the thought is, no, what I want to do right now is I want to see Q cross kappa G. This is just another topological quiver.
Uh-huh.
All that it is right now is another topological quiver.
And can you explain one more time how you associate the topological quiver, the C star of a quiver?
Yeah. Okay, so what we did is we took our data from a topological quiver. We constructed the quiver correspondence, right? So right action comes by precomposition with the source map, left action by precomposition with range map, and then this inner product business. Then we represent by Kuhn-Pimsner covariant homomorphisms, and then we ask what's the universal object for these Kuhn-Pimsner covariant correspondences.
And when it's Kuhn-Pimsner sister algebra, that's what you mean.
And that's what I mean, correct.
Thank you.
Of course. Now, but this was an excellent question. I want to get back to it in 2 slides, I think.
Okay.
So the thing is that we had this co-cycle floating around, right? When we were talking about a skew product, this skew product depended on your choice of co-cycle. And the punchline that I want to give now is that, okay, this co-cycle actually induces a co-action on the C-star algebra associated to the topological quiver Q. And it's given exactly as follows, right? Okay, so we need to take as inputs an element from the C-star algebra of Q, and we need to give an output, which is a tensor product between that C-star algebra and the C-star algebra associated with the group G. Well, what should this thing do? The C-star of Q is generated by what it does on the coefficient algebra A and what it does on the correspondence X. Well, what we would hope for is that this coaction actually does nothing to the C-star algebra to the vertices, because the co-cycle never had anything to do with the vertices to begin with. This is indeed the case. However, if we look at a continuous compactly supported function on E1, and we represent that in our C-star algebra, and we apply the coaction to this element, what it ends up being is you do almost nothing. This should be a 1, not the identity. Sorry about that. It should do almost nothing, except for it should twist it by some kind of an action, some kind of a multiplication on the right, which we think of as being associated with the range map, the way that I've arranged things. What is this map W? This map W is exactly the, under the Gelfand map, the dual to our cocycle kappa, tensor with the identity, and you apply it to this magical unitary, which floats around in the multipliers of the tensor product of C0 of G with C star of G. I don't want to belabor this too much. The point is that this map here really says, okay, give me a point in your group, and I will associate to you the unitary, which is appropriately associated to that point. And then we take, that point and we say, okay, well, what elements in E1 actually receive that point is the idea here. So this really is honestly showing you how the cocycle is appearing in this coaction. And there's a strong analogy by how it is and how we've seen the skew product to be constructed to begin with. So what can we do?
I have a stupid comment, if I may.
Okay.
If I see identity of anything, I immediately think, well, if it's really identity, then identity of anything is anything. So why bother writing it?
Well, once again, so for me, this helps, in my mind at least, to keep track of what leg we're doing things on, because this is the map. The map is KX tensor the identity. So what this map is really doing is it's saying, okay, well, what I want to do, I want to apply a KX to this left
So
leg.
yes,
Parentheses are.
yeah, exactly.
Around.
Yeah, it's, so, yeah, exactly. So now I understand. Yeah, that's what you mean.
Yes, yes, and above, same above.
Yes, yes, exactly, exactly.
Okay, now I'm far more happy. Okay, of course.
Okay. And so, so now what can we do? As I said before, well, when you have a coaction, you can ask, well, what's the cross product of this coaction? Can we delete these now, Piotr?
That's what I'm doing.
Thank you. And so what I want to leave us with is this particular theorem here. It says, okay, well, on one hand, we have this operation on the level of topological quivers where we can construct the skew product. And then we can say, oh, well, what's the C-star algebra, which is naturally associated to the skew product quiver? That's this right-hand side. On the left-hand side, instead, we have a C-star algebra associated to our original topological quiver. And we have a coaction, which is coming from this same skew product, right? The same cocycle. And so we can ask, okay, well, what is the coaction cross product of this thing? And the theorem here says, okay, well, these are actually isomorphic. And here's the way that the proof goes. Remember this map pi that I said that we natively had coming from C star of Q to C star of the skew product. Okay, well, great. This is going to be one component of a covariant representation for the coaction. For the other part of the covariant representation of this coaction, we're just going to take C0 of G, and we're going to map it into the coefficient algebra of the skew product by precomposing with the quotient map. Precomposition with the quotient map is what we do here. It turns out that these two things together give you a covariant representation of the coaction, which means that we get a natural star homomorphism from the C star algebra of the coaction cross product into the skew product. So great, that's step one. We have a covariant representation. It ends up not being so hard to show that this is surjective because, well, really, what are we doing? In one sense, if we're thinking about what the skew product is, really, it's got, this factor which is coming from the original information from the quiver, and it's got this group information. Well, what these maps are doing is exactly recovering on one hand from the C-star algebra of Q side, covering all of the original quiver information. And on the other hand, we're capturing this second factor, this group information instead. So all that remains is to show that this map is injective. And we can get this by an application of the so-called dual invariant uniqueness theorem, which essentially says, okay, well, there's a natural dual action on this C-star algebra. So if we can find a handy action on the skew product quiver's C-star algebra, which is compatible under this map, which is covariant under this map, then you actually get that this is an injection. And it turns out that the right action that we had discussed before is exactly the appropriate action, which induces the action on the skew product, and that finishes us up. And I think that's two things. I think I'm, in fact, 2 minutes over time, and also done with my talk. So thanks for the 2 minutes, and thanks for your attention.
Thank you so much. Okay, any questions? Adam? No?
No, I'm just clapping my hands.
Yeah, just that.
Virtually
Okay.
and also in real.
Okay. Anybody else from Zoom? I don't see any volunteers. Anybody from the room? Yes, go.
Here delta is a coaction which is being induced by the cocycle K. So instead of the coaction, if we had an action which was induced by the cocycle, then do we have an isomorphism from C star of Q crossed with the G hat if G was abelian, Puntrag dual? Because as Piotr mentioned before, in the proof of the K theory of graph C star algebras, the skew product is taken with Z, and we have an like it is exactly like this, and the cocycle is a constant map which goes to the -1 element in Z.
Yeah.
So if we had, we could have
Yeah.
something similar here as well.
Okay, so you're saying we want to assume that the group G is abelian.
Yeah.
Start, right?
And delta is an action induced by the cocycle, and we have a similarly defined cross product C star algebra for the action.
Yes.
So we would have to replace G with G hat in that case.
Yes.
Then you have an action. Yes, yes, all this is true. Yeah, so this directly generalizes what you're saying, because when G does happen to be abelian, then you just apply all of this Fourier transform business and you get the same result. Yeah,
Thanks.
of course.
So this suggests that you could replace this G by a quantum group.
Of course.
Yeah. So G is not necessarily.
Oh, so you didn't mean a quantum group?
No, so it was a group.
No, yeah, G. Well, in this talk at least, G is a group. Yeah.
But nothing prevents you from assuming that it's a locally compact quantum group.
No, nothing comes to mind at all. Yeah.
Yeah,
A lot of this theory should apply much the same. Of course, one of the things, like I said at the beginning, one of the things that I really like about this context, at least, is how very topological all of the structures are, right? You can really see, and you can really play with these topological spaces to really get a sense for how this analogy is coming, and yet still come out with, you know, genuinely non-commutative C-star algebras and see that, you know, our dreams are coming true, right? We can just apply the quotient maps in these appropriate settings and still get what we had hoped for, even in this much more non-commutative setting.
Probably you could even assume that Q, your quiver, is quantum in nature.
Well, there are
Why not?
Yeah,
graphs.
Quantum quiver.
this is kind of this is in my imagination, is that somehow these quivers are a nice example of something that displays a lot of topological data, but the arrangement of it all together somehow is non-commutative in heart, right? The same way that directed graphs are. Somehow the way that that you define the C-star algebra associated with this graph says, okay, well, somehow this is a quantum object because we've got these vertices and these edges and how they're arranged. Same principle. With a quiver, you've got topological spaces together with how they're arranged, and this is somehow a really nice example of a non-commutative or a a quantum space.
Richard, do you want to ask a question? You are unmuted, so maybe you feel like asking a question. No? Okay. Right, so let me ask you something. Two things, actually. One, can you somehow give me Rayburn-Szymański for topological quivers, so that I can say, I give you a topological quiver and you give me the K-theory of the corresponding sister algebra?
Yeah, this is a matter that's taken up in the paper where topological quivers are studied thoroughly. This is a paper by Muley and Tomford, and they do some work to work out the K-theory of these quiver C-star algebras. It turns out that a lot of this work actually generalizes very kindly from Katsura's work. So, of course, Katsura also did work with topological graphs where he was able to discover information about their K-theory. And so I think the short answer to your question is, yeah, this is somewhere out there in the literature. Probably the methods are different, but I don't want to speak too far out of turn and say that I know that for sure.
So I have a suspicion that this approach would allow you to speak about K-homology. Because if you have this Hilbert module,
okay.
Yeah, it's very close to the context of Haifa modules.
Maybe,
yeah.
And my second question is, could you please give me a tangible, concrete example of a finite topological graph, well, maybe not finite, but a topological graph which is not discrete? I would like to have something in my mind, but simple.
Wait, okay, so an example of a topological quiver, which is,
Not discrete, not graph, not the usual directed graph. I want.
oh, yeah,
that's-
well, I had a picture of this one that I gave to begin with. Hold on, we're gonna, this one here on the left-hand side, just
Oh,
take
okay.
a plane.
Or just a plane, okay.
Yeah, just take a plane. That's a very simple example, which is it's not a directed graph to be sure. It's not even a topological graph in the sense of Katsura because this bundle projection is not a local homeomorphism. So it's genuinely different. And so you can get a lot of distance just by thinking about, Cartesian products with non-discrete spaces.
And your topology is the usual boring Euclidean topology.
Yeah, sure. Yeah, and then you could even get more as exotic as you'd like after that, as long as you obey all.
Niminsky half plane, yes. Yeah. Okay, so if there are no further questions or queries or comments, let's thank Lucas again. Thank you so much.
Oh, the pleasure is mine. Thanks again for the invitation and all the work in organizing this.
Let me stop the recording.